Um, what we've talked about before, up until now, and we'll make a change from that today, is what we've kind of referred to as the first 2 weeks or first 3 months of transport. I'm not sure it even takes that long, where everything is driven by gravity and is controlled by this balance between gravitational forces driving downwards flow of these components, either their buoyant weights or their absolute weights if they're in air, um, and resisted by capillary forces, which we think are quite large because they can hold these things in place against very large pressures, as we found out for Yucca Mountain. And so this has just been our attempt to be able to look at basically a force balance. And that really allows us to describe, if I zoom back through this, I guess I didn't get the page number to start with, but this first view, it allows us to describe why these characteristics exist in terms of L naples on the top and D naples on the bottom. And in terms of, let's plug this in, should be helpful, why we end up with this lens that sits here that's, if you like, buoyed by the water that it sits on because it's less dense than the water it sits on, and so it doesn't go anywhere. It's cradled, if you like, by it. Why we have this chimney of smeared material that goes down through here, and how we might be able to say something about the saturations of this from our capillary pressure versus saturation curves. And also what happens when it goes through the water table, where it's denser than water. Again, now where it's buoyed not by the water table, but where it's buoyed by this capillary barrier, which will stop it from penetrating. And again, as we go up through here, we can imagine that we have kind of a smeared chimney with the saturations getting slightly larger as we go down deeper. And all that has been based on our understanding, if you like, of capillary behavior, and is epitomized, if you like, in this one figure that we spent some time on last week that says something about how saturation should change as we go up or down. If it's a D napple, then the saturation of the D napple phase would be this part here, and the saturation of water would be the remainder. And if it's above the water table, then this would be the saturation, again, of the non-wetting phase. This is the non-wetting part. This is the wetting part. This is the non-wetting phase, which in this case is air. And the wetting phase would be the water. And so it's entirely logical that we should evaluate from these the relative saturations as we go up or down through here. And it's really predicated on the difference between the, whoops, didn't do that. This between the pressures in the two potential phases. The water in one case, which would be less dense, and the denser napple in the other case. It's just the difference between these, which is really prescribing this capillary pressure. And it's this capillary pressure which we can scale to go vertically. And indeed, capillary pressure scales with depth in this particular case. So this has to be a linear function. So you can imagine just stretching this, this capillary pressure versus saturation diagram, anchoring it on the surface and stretching it down to be able to fit. And so that's been the sum total of our activities so far. But it's a useful figure to be able to understand exactly what's going on. And in terms of behavior, it represents the behavior in aggregate, in that what we would do is we would take a, do this, make this larger, I guess, make this larger. What it allows us to do is basically take a volume that would contain this. If you look at the relative areas of red versus white, or clear rather, maybe it's 30% red and 70% white, and so those would be, roughly speaking, the relative saturations of these systems. And so since we actually have those proportions here, we could, if we wanted to, go back and look at the case where we have 70% water saturation and 30% napple saturation. So I guess 70% water saturation would be something like this. This would be 70-30. And so we could imagine that the capillary pressure in that should be something like this. That's really all we're saying. And so capillary pressures are an average saturation, if you like. Obviously, if you look within the red part, then it's 100% NAPL saturated. If you look in the clear or blue part, then it's 100% water saturated. But in this individual block, which is our sample, if you like, it's partially one or the other. So anyway, so this represents an equilibrium behavior. Nothing's moving now. It's gone to this, it's got here within some period of time, and now it's sitting here, and it's stuck because the forces in these relatively small capillaries are really high compared to the gravitational forces, which are in balance. Gravitational forces aren't changing because gravitational field isn't changing, and therefore it's stuck there. It doesn't do anything. The only thing that will happen is that potentially it could move if we put a change in pressure across it. So if we put a change in pressure and say we increase the pressure from this magnitude that we got here, and we increased it by some amount, which we'll call delta P, then we'd end up at a new saturation, so it'd have to physically go along this curve to get there. And so we can change that pressure in two ways. We could make the column of red stuff above it higher, and so that would drive an increase in the capillary pressure, and therefore drive it. Or we could change the boundary conditions, say the fluid pressure just in the water that's around it, and try and make it flow out. And so that second part is really what we're going to turn our attention to now as we look at no longer static behavior, which everything we've done to date has been dealing with that. So now we're no longer talking about static behavior. And so we're talking about what happens when we try and get these fluids to move. And so that's the crux of what we're dealing with. And what's the best way to deal with this? Okay, we could use the slides we have, but let's not. So the basic behaviors that we would like to talk about, now actually let's use the first slide to go through something. So here's the basic idea. We have a porous medium which might look in reality like this, which is partly red and partly green in this case instead of the bluish color. I guess no, it's the other way around. The green is the non-wetting fluid and the red is the wetting fluid of water. And so it's quite happy to sit there and not change saturations, and that's if the difference between the pressures in the two fluids are not changing. If pressures in the two fluids are not changing, we could actually still remove some material from here by putting an upstream pressure. So in other words, if we were able to apply a pressure on this upstream face relative to the downstream face, so that as we looked across it, we can call it delta P, and we'll call this length L on the bottom. So the gradient that we're applying is dP dx, which is really the same as a change in pressure as we go from upstream to downstream over some length. And so instead of thinking about this system where we have these irregularly saturated components, where in this case the non-wetting fluid we would expect to occupy the biggest pores first, right, because of the bubbling pressure arguments. So in other words, we've said that if we look at capillary pressure versus saturation of water, then it looks something like this. If we apply this particular pressure here, then it occupies the biggest pore first and fills it, and then as you increase the pressure to some slightly larger amount, it will occupy the next smallest pores and smaller pores. So in other words, the green fluid here is occupying the largest pores. So imagine now that we could centrifuge it somehow and get all the big pores that contain the green fluid down at the bottom of the sample and the little pores with the water at the top of the sample. And the fluids would migrate in the same way. And so now if we applied this pressure across here, we would actually get flow coming out of here by flow within the fully saturated porous medium that has the red fluid in it, the NAPL, the non-wetting fluid. And also the green fluid would flow because they're connected between the upstream and downstream. And that we know from Darcy's law that the velocity of flow is typically given by a hydraulic conductivity, uppercase K, times a change in gradient, hydraulic gradient. And we'll write it this way for now because you may have been more familiar with that. That's if you took 452, that's more likely the way you saw it. And so in this case, if you were collecting fluids from this, you'd collect both the non-wetting fluid and the wetting fluid on the downstream side by applying this pressure gradient across it. And what we'd like to be able to do is be able to figure out exactly what those rates of flow might be, because we'd like to be able to stick a straw into this and be able to pump out the green fluid to be able to remediate it. That's one of our goals. And so that's what we'd like to be able to do. If we're not changing the saturation of the system, so in other words, if the proportions of the wetting fluid and the non-wetting fluid stay in these proportions, then there is no effects of this interfacial tension that we've seen. The only effect would be in keeping this boundary in place here, but there would be no drag on this by Capri forces because it's 100% saturated with the red fluid, and therefore there are no interfacial forces in this. So we only have to actually worry about Darcy's law in governing the flow through this. If we do take out, for instance, more of the non-wetting fluid, if we take out, for instance, more of the wetting fluid than the non-wetting fluid, then by definition, if we're removing more green than red, then the red has to increase its volume, right? Because we're taking out more green than red, then by definition, more red has to flow in to be able to replenish it. And so you could imagine if we're changing the relative volumes and changing the space that's invaded, you could imagine that the distribution of the saturation would change. And so in this case, if you put a pressure gradient across here, you're getting both the non-wetting fluid and the wetting fluid out of it, which is the same as this middle component, which is really the same as this, right? But if you, for instance, took more of the wetting fluid out and replaced it with non-wetting, you'd end up with this. And now if you have this pressure gradient between the upstream and the downstream, what is it you expect to get out of the downstream portion? You expect only to get the red fluid, because this is the only one that's simply connected as you go across from one side to the other. This is completely isolated, and therefore you're really only putting a pressure within the red fluid, both upstream and downstream, and the green fluid basically isn't feeling it. If the opposite is the case, where you filled your aquifer mainly with water, then the NAPL is in exactly the same condition, the opposite, I guess, the reciprocal case from this. Now you're going to create only the green fluid through here, because now there's not a connected pathway that gets from the upstream face to the downstream face with this red fluid. And so clearly we're going to have to be a little bit sophisticated about how we figure out exactly what the effective transmission of these fluids are. So in this case, only red fluid comes out. In this case, red and green come out. And in this case, only green come out. And so those are the rules that we'd like to be able to establish to be able to basically use Darcy's law to be able to figure out what's going on. Okay? So how do we do that? Well, the simplest way is to be able to think of a sample or a core plug or a sample from the aquifer, which is this cylindrical sample. And we can think of it as being filled with these two different fluids, the green one and the red one, partly, centrifuged as we've talked about before. But let's do something else first and be able to make a connection in terms of Darcy's law. So we said a little bit about Darcy's law, but let's say a bit more. So I don't remember the dates now, but Darcy's law comes from Henri Darcy, who was a public works inspector in the town of Dijon in France, and noted that if you doubled the pressure in the fountains in the town, the fluid came out twice as fast. If you quadrupled it, it came out 4 times as fast. So he established the fact that there was this relationship between the driving pressure that you apply to the amount of volumetric flow that you get out of the system. And so the simplest geometry in which to define Darcy's law is one that basically takes a tube of material has a pressure measured at the downstream portion, has a pressure measured at the upstream portion, and typically rather than pressures, we might measure heads. So in other words, the pressure here, but this is relative to some datum. Z equals 0, that this here is equal to Z2, this is equal to H2, which is equal to whatever the pressure is at the bottom divided by the unit weight of water. And at the upstream portion, very straightforwardly, this is the elevation Z1, and the pressure head that's driving flow is this H1, which is again equal to whatever the pressure is that you'd measure at this particular point here, divided by the unit weight, in this case of water. And Darcy's law was merely to say that the volumetric flow rate, Q1, you could write as the cross-sectional area of this flow, which we'll call A, times hydraulic conductivity. This is in meters per second, or length over time, times a gradient in head over some length. And this length is just equal to the length of this particular, oops, didn't need to do that. The length of this particular tube. So it's filled with sand. We can get a volumetric flow rate out of it, and it's a function of the cross-sectional area, hydraulic conductivity, the head, which is the sum of these, and I haven't left myself much room, but let me put this, that H2 is equal to the elevation of point where you're measuring it, plus the pressure head at that point. And we could also write the velocity squared term over 2g, but usually this velocity term is so nominally infinitesimally small that we don't care about it, we throw it away. And so we just work with those other two. And so that allows us to be able to say exactly what the flow rates through the systems are. If we know that the flow velocity is equal to the Darcy velocity, V sub d is Darcy velocity, is equal to the volumetric flow rate divided by the total cross-sectional area, then we end up with the Darcy velocity being the hydraulic conductivity times the gradient that drives flow. Nothing more than that. It ends up being typically taken, I guess the other way we could draw this would be to draw it a little cameo below this. And so if I draw this height H1 and I draw this height H2, so in other words this is just H here, and I join those two up, then basically this change in the elevation of these two components, I know that this is kind of sloping, but don't worry about that. The change in these two components, dH dx, is the gradient that drives flow. And usually, since you know that water flows from high potential to low potential, the flow direction, in this case, must be a velocity in this direction. This is in the negative direction, and so a minus sign goes here. This is a positive gradient, arranged like this. This is in the positive quadrant in terms of calculus, and so this minus sign merely accounts for the fact that a velocity is really a vector, and it has not just magnitude, but it has direction as well, and it's in the opposite direction of the x direction. Okay, so that's Darcy's law, as you've seen. What we can also do is that now that we've defined exactly what hydraulic head is, which is this term here, we could also resubstitute that term into here. So if we substitute this head into this as the elevation plus a pressure chain, a pressure divided by the unit weight of the fluid that's flowing, then what we get out of this is a new Darcy's law, or just, it's not a new Darcy's law, just written a different way, is that this is now hydraulic conductivity multiplied by this derivative of this, sorry, not head, is it? It is head, because this is it here. But if we write it out in terms of the two components, actually let's write it out in terms of the change in z plus the change in pressure with length divided by density and gravity. That's just this. This is just rho g. And so I haven't actually done anything other than substitute in the values of this. And the reason for that is that most groundwater hydrologists are happy to write the behavior in terms of head gradients driving flow. When you start dealing with multi-phase flow, with more than one fluid, it's much more convenient, almost essential, to be able to work in pressures. But we can't just substitute pressure directly in here because we have this elevation component. And so if the other transformation we make is that another separate piece of information is this kind of important relationship. Hydraulic conductivity, density of water, gravity is equal to permeability divided by dynamic viscosity. So I guess I could write those things. This is permeability. It's in units of meters squared. This is hydraulic conductivity. It's in units of meters per second, length over time. This is what? Dynamic viscosity, I guess. And it's in units, SI units of Pascal seconds, if we're consistent. Density is kilograms per meter cubed, and gravity is meters per second squared. But I won't write those down. And so the reason for doing this is that now I can try and, so what I'm going to try and do is rewrite this in some slightly different form. And so what's that different form? I guess I could multiply, okay, I could divide both sides through by rho g. And then I have to multiply this by rho g. Then I have to multiply this by rho g. So all I've done is multiply top and bottom by rho g. Getting a bit crowded, but at least you see now that this term here maybe looks a bit familiar. And so we could substitute that Darcy velocity is equal to minus permeability over viscosity. So all I'm doing is switching out one side for the other because I now have done this. And multiplied through by a term which is density of the fluid times gravity and the change in how the distance in the vertical direction changes with the distance in x. Sounds a bit esoteric. And in this side, these two things cross out. And this is change in pressure with length. And so that's Darcy's law now written in pressures. And so what we could do is, if you think about exactly what the coordinate system is for this, we've kind of implied that the z direction is vertically upwards and the x direction is horizontally across the page. So by definition, if that's our coordinate direction for this, then if we go the component, a small component in the z direction relative to the x direction is 0 because they're orthogonal to each other, right? a small piece of x has no component that's in the z direction. So by definition, this term in this particular arrangement is equal to 0. And if that's the case, then we have just a much easier relationship, which is that Darcy's law looks like this, because you throw your... And that's all we need in most circumstances. But if, instead of flowing largely with this tube in the horizontal direction, we arranged the tube so it was vertically upwards. And so now the direction of flow in x would also be arranged in the same direction as gravity. And so this term now would no longer be equal to 0, because one component of x would be one increment of z. And so it would be equal to 1. And so we'd have to add this extra term on, and we have to take care of it. And so we don't need to worry too much about that in this class. But if you like, the physical explanation of this is the swimming pool explanation. So you take a swimming pool, and the swimming pool has water filled up to the top. You look at how pressure changes as you go down in the swimming pool. We'll draw z positive downwards. You know that the pressure changes in the swimming pool as what? P equals difference z multiplied by the unit weight of water. Or you also know that the change in pressure with elevation is just the derivative of this. I guess it would be a minus. No, it would be plus. Now, let's do z upwards again. So this is negative. This is positive. If we do that, then this is true, and this is true. And so now we know that if the water's sitting in a swimming pool, it's not circulating, it's stagnant. You fill the swimming pool up with sand. Still the same pressure profile as you go down with depth. If we think that then we look at a cylinder of sand in here, then from the Darcy velocity being equal to the permeability of the sand, the viscosity of the water, and the change in pressure with elevation, minus. This is just a constant. It's finite. It's not 0. This, by definition, is the unit weight, and so this is non-zero. So this says that in this particular case, there has to be flow that's going upwards in this system, and it's not. We know it's not. It's just stagnant, and it's registering the fact that the fluid pressure has some linear variation with depth, because as we go down, we have more stuff sitting above us progressively, and that's really what we're feeling. And so the idea between this expression here, the fact that we have this initial component here, if we're looking at vertical flows, is merely to account for this stagnant component. If by some miracle the pressure in here was increasing slightly faster than this static amount, then it would be this overpressure, this delta P, that would be driving flow. And so if you wanted to plot how pressure changes with depth, it's only if the pressure at this lower part is larger than the hydrostat that's going to be flowing uphill. The other way to plot it, I suppose, would be to plot, if you plotted head with depth, you can use our expression for head, which is hydraulic head is equal to elevation plus P over unit weight. And if you plot head with depth for a static swimming pool, it would be this curve here. If you look at the head at this point, or if you look at the head at this point, or at this point, if it's a static fluid, not moving, then it would just be this. If, by some reason, the head was increasing with depth, then by definition, it has to be flowing up. If, by definition, the head was decreasing with depth, then the flow within the swimming pool, or the porous media within the swimming pool, would be downwards. And so just as in this case, if the pressure is larger than the hydrostat, it's going upwards. If the pressure distribution with depth was lower than the hydrostat, then by definition it will be flowing downwards. And if it's equal to it, it's not going anywhere. So to remove confusion, that's exactly what this expression, which really should be in Darcy's law, but often we omit it because we think we're just flowing horizontally. But if you're flowing vertically, you have to actually take account of it. So I don't know if that's clear or not, but the reason is basically the so-called, well, I call it the swimming pool effect. I don't know what anyone else calls it. Okay? So it's not crucial that you understand every single component of that, but it turns up here. It's much easier than this discussion on this page. So that's the first part, is that we can define behavior in terms of characteristics of the unit weight, the self-weight of the system. So we said before that what we'd like to do is be able to now make a stab at understanding how we might get a couple of different fluids flowing at the same time. And so now what we'd like to do is to know how much fluid we get out of the other side of this if we apply a pressure, the same pressure in the red fluid and the green fluid upstream relative to the different downstream pressures of the two fluids, which is the same. So the same gradient across both of them. So again, our easiest way to do this is to kind of centrifuge our system into this so that we have our core split by the two regions which are saturated by the two fluids. And that's kind of what this sample is showing here. And if we're just horizontal, we don't have to worry about this self-weight effect. And so what we could do is we could write Darcy's law. And we could write Darcy's law for the whole, for say, region 1. And what would that be? It would be equal to the permeability of fluid 1 within region 1 divided by the viscosity of that fluid. So all I'm doing is I'm taking our, if I skip back here, all I'm doing is I'm taking this relationship here. If we multiply both sides by an area, then this will be a volumetric flow rate. So that's what I'm doing. So I'm going to multiply it by an area afterwards. Should have done it before. It's this cross-sectional area A1, which is green. And the pressures driving flow across here are the pressure in fluid 1, the green fluid, divided by the length over which it goes. So this is Darcy's law. I guess we could put a negative sign here if we want to. It loses its meaning when we talk about Q's often because we talk about those as scalar values, in or out as being the positive or minus rather than the vectoral quantity. So, yeah, okay. So this is the amount of fluid that's coming out of the green part. If I wanted to, I could also define the total area of the end of this as being the sum of the area filled by the green fluid and the area filled by the red fluid. So those have to add up to the total. And if I did that, then what I could do is I could multiply both sides of, or top and bottom, by the total area. And so now, if I write this out, again, it's the volumetric flow of fluid 1. It's equal to the permeability, no, sorry. Let me write the area first. Let me write the area A1, A rather, the ratio of A1 over A, the permeability to fluid 1, and I guess the pressure gradient over length. And so this is an important expression, because what it does is it tells us how much of this, in this particular case, the green fluid is coming out per unit time. It does it for the whole of the area of this end, but it has this proportionality between the two cross-sectional areas that are present here. it also does it in terms of a permeability of the one fluid which is in here. And so I should also make the case that K1 is exactly the same as permeability. Permeability, if it's permeability to air, or if it's permeability to gasoline or to water, it doesn't matter. The permeability is a function of the material, not of the fluid that's flowing in it. The properties of the fluid that it's flowing in it are taken care of, and I'll add this one subscript to this. And so we could write this merely, we don't need to worry about the fact that this is fluid 1. And so what you recognize here is that this ratio of A1 to A is really the ratio of green to the total end of this. And if you look at this, it's the ratio of green to the red. And so this ratio, what is it? What would we call it? The ratio A1 to A is basically the saturation of fluid 1. It's nothing more than that. And so what we can do is we can replace this as the saturation of fluid 1. And so now, if this is the saturation, this we've already said is just actually equal to the permeability of the porous medium, not to any particular fluid. Then we end up with a new parameter, which is this. If we do the same for the second fluid which is coming out, then just by, I guess, inductive reasoning, the flow that comes out through Q2 is going to be minus the total area. It's going to be the saturation of fluid 2. It's going to be the permeability divided by the viscosity of fluid 2. And it's going to be the pressure change divided by the length. And so what we've done is be able to write an expression to be able to describe this behavior. This is Darcy's law. And so we've written it now in 3 forms. 2 forms, I suppose. No, actually 3. This is form 1. This is form 2. And I suppose what we could do is we could write it as form for the total value Q, which is equal to the sum of those 2 components, 1 plus 2. And I'm not going to write it out in longhand, but I'm going to write it out in the same way is that if the core was just a black box, we didn't know that there were 2 fluids in it, we didn't know what the proportions of the saturations of those 2 fluids are, we would write it in some way as being equal to the area multiplied by some relative saturation times a pressure drop over length. I know I'm getting a bit crowded here. And so this, if you like, would be some function of the permeability of the system, which we think we know. It's not a even though it's a mixture of 2 fluids. The viscosity, well, I guess it has to be a mixture of 2 viscosities in some way, so let's not worry about that for much now. A pressure drop across the system, and an area of our core, which we know, and a relative permeability. And so what we'd like to be able to do is we realize that we can write, if you like, the product of this saturation times the permeability is really what we'll call a relative saturation and a permeability. And it will become apparent what I mean by that in a second. So in other words, the one component we really need to know in this that relates to how much of this second fluid is coming out is to have a parameter which we will call relative permeability that we multiply by the actual permeability, the single phase permeability. So you flow air through it, you flow gasoline through it, you flow water through it, you get one number, which is the permeability of the porous medium. If we multiply it by this new number, then it gives us some idea of what the relative proportions of flow out of the system are. And that's about the cleanest way I can make this case, and you see at the bottom. So the effective permeability is a function of these 2 components. The single valued permeability for flowing any fluid through it, any fluid, air, water, gasoline, the relative permeability to that fluid gives you an effective permeability. And so you can always, you can always calculate the flow of fluid 1 if you know the cross-sectional area, K1 over mu1 times the change in pressure with length. And you can always get the volume flux of the second fluid if you know the total area of your sample and the effective permeability of fluid 2, the viscosity of fluid 2, and the same pressure gradient. If you add these together to get Q1 plus Q2, should you want it, you'd end up with a total volume. And so this is basically the idea of relative permeabilities. And so always we can get this magnitude here, that this effective permeability is going to be equal to a relative permeability and the actual permeability to a single fluid. Likewise, this K2, the effective permeability to fluid 2 is always going to be a relative permeability. I guess I should put a 1 there and a 2 there, and multiplied by the actual permeability to any single fluid. And from what we've said about this up here, you could surmise that the magnitude of this relative permeability is pretty close to the saturation. And so this we could think of as being roughly saturation of fluid 1, and this we could think of as being roughly the saturation of phase 2. Okay? And so what would this relative permeability look like if we drew it on a graph? And the graph we might look at would be this. This is the saturation of water on the bottom. It goes between 100% water saturated and 0. If I hadn't run out of space here, this is the non-wetting saturation at the top. It goes in the opposite direction, right? From a 0% non-wetting saturation and 100% water to 0% water and 100% non-wetting. And what we're going to plot on here is relative permeability. I wish I could get my writing back. I always thought it was much better. Well, doesn't matter. Relative permeability, which we're going to call K sub R. And there are two of them. There's one related to phase 1, and there's one related to phase 2. So what is this graph going to look like for relative permeability if it's proportional to S1 for the wetting phase? So what did we say? So green in our particular case is 1, which is equal to non-wetting. So this is the non-wetting one. So this will be equal to 100% when it's 100% non-wetting saturation. So I think that's this point here. And when the non-wetting saturation is 0, the relative permeability is going to be 0 as well. So this vertical scale is between 1 and 0. And it's just going to be linear between them. And so the relative permeability to the non-wetting fluid is going to be this. When it's 100% water saturated, the relative permeability or saturation of the non-wetting component is 0, so it should have no transmission. When it's 100% non-wetting saturated, it should be just as if it was a regular material that's saturated with that material, so it should be exactly equal to the permeability, which we're multiplying by. Okay? If we look at the red one, this is the wetting saturation. The wetting saturation, when it's 100%, will be 100% saturated, so it'll be this point here. And when it's 0% water saturated, then the relative permeability, which is equal to that, will just be zero saturation. So this will be this curve here. And so this would be the permeability, relative permeability of the wetting saturation. So it's just this so-called X diagram. And that's really what we're doing. So we've said that we can take a core, we can centrifuge it somehow magically so all the pore space that contains the red fluid and green fluid separates themselves. We can look at flowing fluid in each of those separate stream tubes. We could actually pull the core apart, if you like, into the red and the green part, so long as we know the cross-sectional areas. We can look at the amount of flow that comes out of each of them, and it should in some way be proportional to the cross-sectional area that's filled, which should be proportional to saturation. And then we can use that now to be able to draw a diagram that represents the relative permeabilities of these things, and it will look basically like an X plot. And so that's basically the derivation that we've gone through to be able to get to this. And so if you think about what these relative permeabilities should look like, this is a plot that you could imagine is what they might look like. We've drawn it slightly differently. This is our saturation along the bottom. So in this particular case, was it red? Yeah, red is our water. 100% water saturation would be 100% red. If you pump fluid out of it, all you'll take out of it is red fluid because the green fluid isn't connected. And so the relative permeability to the wetting saturation should be this point here. When it's all NAPL, the saturation of water in the limit, the red goes to 0. The relative flow that comes out due to water should be this point. And so I don't know if I want to leave this on here, but this plot would look like this that we've just drawn. I'm going to take that off because I just don't want to complicate it. Likewise, if we look at how much green fluid is flowing out of it, 100% saturated in green fluid would be this point. There'd be no fluid in it at all, and it would be transmitting only green fluid. The relative permeability would be this term up here. Once we get here, there's no green fluid, and the point here would be this, and the relative permeabilities that we just drew would look like this. And that would be our behavior. So in other words, the plot that we had before, someone's calling me, sorry. Daughter, never mind. She's probably still alive. She'll survive. House could be on fire. So this is saturation of water, 0, 1. Saturation of non-wetting, 100% non-wetting. This was this, and this was this. Whoops. And this was K sub R for each of these. So it doesn't quite look like this. What it does look like is this. So this plot that we have here does this. We'd expect it to go to this point somehow. So I've just drawn, instead of this line here, I've drawn this. This would be the saturation of which phase? 100% water, the relative permeability is 100%, and remember that the effective permeability is equal to the relative permeability multiplied by the actual permeability. This is constant, and this is the only thing that changes. The effective permeability to the second phase, my writing's much better here, I must be leaning somehow differently, is the relative permeability of phase 2 multiplied by the same. These are the same. But this is just a scalar, which is a function of saturation. If it was equal to saturation, it would be just a linear curve. If it's actually a function of saturation, which it is in reality, then this X plot changes to look like this. So this is K effective permeability for the wetting phase for water. This is the curve for the non-wetting component. Still goes through these kind of endpoints, and this is relative permeability of the non-wetting fluid. So when it's 100% not wetting saturated, it basically has the permeability of the pristine virgin permeability, if you like. It's not, none of the space is occluded with the other fluid, so it has, you'd expect it to create the fluid. Ken?
How do the units work out in that equation? Because you have an effective permeability time equals a permeability times a permeability. So I expect it to be a squared permeability.
So, well, yeah. Okay, it would be, except that the units of the relative permeability are between 0 and 1 and have no dimensions. So they work out fine. So,
the 1 is unitless.
Yes, this is unitless, dimensionless. Yeah, good question. So relative permeability, these terms on the vertical axis here, like saturation, vary between 0 and 1 and have no units. Yeah, so it's not a square. So it returns whatever the units are of each of these individual values. Okay. What else do we need to say? We've shown these initially only in this central portion, so it's excluded on this portion. And you can imagine why that might be the case. Let me draw something on this. And so it's useful to think about it in this way. And thinking about it in this way, where are we? We're 2-4, right? Multiphase flow. So the two most important diagrams that we'll deal with in this early part of the class are the one that we just drew, which I'm going to draw again, which is this relative permeability chart. And above it, I'm going to draw our capillary pressure versus saturation curve. They both have the same axes, which are the saturation of water from 0 to 100%. And if you like, the saturation of the non-wetting is the opposite, from 1 to 0 in the opposite direction. Same axes for both of these. I guess this is also saturation of non-wetting between 1 and 0, saturation of wetting between 0 and 1. So they're the same diagram so far. But on the vertical axis of this is relative permeability between 1 and 0. This is going to be capillary pressure between 0 and some, I don't know, not necessarily 10, but some number other than, it's not limited 0 to 1. And then these limiting values that we have. And so let's put these ordinates on here that we've talked about. This, if you recall, is the irreducible value of the non-wetting fluid. So in other words, this is the amount of NAPL that we're always left in even after we've tried to drain it out. This is the irreducible magnitude of the of the wetting component. Right? And you'll remember this. This is our capillary pressure versus saturation curve. This is our drying curve. We dry out the water. We're reducing the amount of water as we go up here, increasing the amount of air or the NAPL. This is our imbibition curve because we're sucking water back in here, but we can't get to 100% water saturated because we have this amount of NAPL left in here. And if you remember from the two curves that we just looked at, let me draw these quite deliberately. So this is kind of a dead zone here, and then it goes up to some magnitude. And this magnitude here is lower than the magnitude on the other axis. Let's talk about that. So this does this. And if I flip between these, I'm going to come back to it. If you remember this curve that we had before, this curve here and this curve here were limited by these extrema, if you like. They couldn't get beyond this. They're kind of shuttered by these. This one goes up to this point here, but notice that this elevation of this point is less than this one. And if you look at this, this is just the summation of these two curves. So these two curves, if you add this height of this curve here to the height of this curve here, you get this point here. That's all this dashed line is. Not very important. I guess it's only important to make the point that if you add the two relative permeabilities, even though the two saturations always have to add to 100%, the actual two relative permeability values are much less than 100%. This curve here. Okay. So let's go back to our crude drawing of this. And let's understand what's going on here. This is what? PC0, our bubbling pressure. So here we're 100% water saturated, our relative permeability, and this is our relative permeability to what? Water or NAPL, this one. Well, since we're 100% water saturated and it gives a relative permeability of 0, it's probably not the water one. I was going to say water, but it's not. This is the non-wetting. And here we think, we're not quite sure exactly how this might go through here, but we expect it to pass its way up to this point. So this here has to be the relative permeability of the wetting fluid. When it's 100% water saturated, the relative permeability to water is 1, but the relative permeability to the NAPL is 0, because there is no NAPL. When it's 100% NAPL saturated, the relative permeability to the NAPL is 100%. Relative perm is 1. There is no water in the system, so the relative permeability to water has to be 0. And so what it is a way of being able to calculate the amount of water that we get through the system. And so just to reiterate, we can always calculate the volume of fluid 1 as being equal, I guess let's do it as fluid I, as being equal to what? The total cross-sectional area, the relative permeability of phase I, the actual permeability of the porous medium, the viscosity of fluid I, and the pressure gradient across it. That's a basic expression. Units perhaps might be worthwhile mentioning them. This is meters cubed. This is meters squared. This is none. This is meters squared. This is Pascal seconds. So newtons per meter squared times seconds. This is pascals. And this is meters in SI units. So you can check that it's dimensionally homogeneous as it should be. And so that is basically how we can calculate how much gasoline comes out of your sample if you apply an upstream pressure to it relative to a downstream different pressure over a length of the sample for a known permeability of the sample, given that you know the viscosity of the gasoline, if you know the relative permeability of it, which is a function of saturation, or if you don't have saturation, I wish I had different colors. The other way to draw this curve is to draw it as an X curve, slightly differently from before. Instead of putting these through the ordinate up here, just going through these irreducible saturation parts. So let me undraw it that way, because it's just complicated matters. So in other words, we could draw it as a plot that looked like this. These are the no-go zones, and so the relative permeability plot could look like this for the two fluids. And we will use this in one of your examples. So in other words, we don't do it as an X right the way to the top and bottom corners, but we do it slightly steeper, and we have it hit the boundaries at these irreducible saturation zones for reasons that we can think of here. Why might I have deliberately drawn this permeability here lower than this one? Relative permeability. It's the permeability for the wetting fluid. Any thoughts? Well, it's kind of related to this, right? So, we're kind of running out of time. We talked before about these curves, right? If we had a capillary pressure curve that looked like this, then it means that as soon as we get to this pressure, it fills up the pore space that has this size, and all the other pore spaces must be the same size because we fill them up and fill up the whole medium. And so when we put the non-wetting fluid in, it fills up the largest possible pore first. So the non-wetting fluids occupy the biggest pore space. So the non-wetting fluids, which this is the non-wetting fluid, even at relatively small saturations, occupies the biggest pore throats. The biggest pore throats, we don't know this yet. Actually, you do from fluid mechanics. You know that if you think about a tube, the flow rate along a tube is proportional to the diameter of that tube to the power 4 times the pressure gradient. Or it's proportional to the area of the tube times the diameter squared times the pressure gradient. I don't expect you to remember that. But it means that if the non-wetting fluid fills the biggest pores first, then these are the ones that give it the biggest permeability because fluid can flow much faster than that. And therefore the non-wetting fluid has kind of a higher relative permeability, which of course is manifest as an overall larger permeability in the sample. Basically because it fills up the big pores first. The water fills up the small, only occupies the smaller pores as it's displaced from the bigger pores, and therefore it's a lower permeability. And I didn't draw it on here, but the other curve you could put on would be this ensemble curve, which is, I think, the relative permeability of the non-wetting plus the relative permeability of the wetting. And it's different than the saturation of the non-wetting plus the saturation of the wetting, because we've always said that this has to equal 1. And obviously, if you added them together, then that value on here would be the top. And so it's interesting that a porous medium that has one fluid in it is quite efficient. A porous medium that has another fluid in it is quite efficient. The relative permeability is 1. The porous medium of the fluids that has 2 fluids in it is much less efficient because the relative permeability of that is really sitting at this point here, which is much less than this 1 value. And the reason for that is that it's got this tortuous flow that it has to go through to be able to get from one side to the other. Can't just get there straight across, as in our centrifuge geometry, flowing straight across, in which case it would be. It has to go on this tortuous flow path that gets through the system. And that's why it doesn't add up. Okay? So that's all you need to know maybe about permeability. And it's all predicated on the amount of volume that we fill up with the different fluids. You can look through these other materials, but the key figure, I think, is this, and understanding how it works. And so I'd say that the main key understanding point are the points that are on this. You need to know Darcy's law written for 2 fluids. You can write it for fluid I, fluid 1, or for fluid 2 just by substitution. And you get the appropriate results. So it allows you to calculate how much fluid you move through the system. Okay?